So, good afternoon, everybody. Welcome back to the last Quantep seminar of the year. And today it's a pleasure to introduce Christian Bauer from the Lawrence Berkeley National Laboratory that will present some recent work of his group on quantum simulation of effective field theories. Please, Christian, welcome, and the floor is yours.
Thank you very much. It's a great pleasure to be here. I wish I could at least be in the same time zone, but it will take me 2 more days. I'm flying out tomorrow to Europe. But anyways, very good. Yes, so I want to tell you a bit about quantum simulation of effective field theories. And this is mostly based on a paper that I wrote with Murat Freixes and Benjamin Nachman, which is published here and then PRL. But I'll mention a few other things at the end of my talk as well. So, I don't have to tell this audience what the standard model is and how successful the standard model has been, but, suffice it to say, we have an incredible theory that describes the most fundamental interactions of nature that, of course, culminated with the discovery of the Higgs boson more than 10 years ago at CERN. In order to do these experiments, we work an experiment like CERN. Here you see the tunnel, and to truly understand the standard model, and the main issue that we're having, that we know that the standard model, despite all of its successes, is incomplete. There's many observed phenomena, most prominently dark matter, that we know exists in our universe, but we have no particle in the standard model, or the standard model is not able to describe it. And there's other things like the baryon, anti-baryon asymmetry, and so on. So we know that the standard model is not actually describing all of nature. And this is part of the reason we're building experiments like the Large Hadron Collider and so on, because we're hoping to find extensions of the standard model. So that means we want to compare an experimental observation over here, say from the Atlas experiment, against the predictions of the standard model. And that, of course, requires us to connect those two, to really make a calculation of the standard model, really for observables that look exactly like what we see in an experiment. And what we see in an experiment is really fully exclusive events. So ideally, what we'd like to be able to do is go from the Lagrangian of the standard model to really predict fully exclusive events at experiments at the LHC, for example. This, I think, is one of the holy grails of high energy physics, is a full simulation of a scattering process at colliders. So by that, I mean really produce or simulate from all energy scales, from the shortest energy scales here, all the way to the hadronization and decays afterwards. This is something that is not possible at all at the moment from first principles. We have various tools at our disposal, in particular parton showers, that do actually give you full description, but they use, at least mostly for the long distance parts of this process, they use phenological models. And so this is not a first principle calculation, so that means we have really no real control over the systematic uncertainties in this process. And I think if we could really do this from first principles, that would really change how we do particle physics, because there's many observables at the LHC that we don't use because we don't believe we can predict them. So the dream would be to literally compute the full S matrix, and the full S matrix is literally describes the process at the LHC. So to compute a process, say, how do 2 protons produce a given final state X? What I need to do in the S matrix, I would need to create an initial state with 2 protons at some initial time very, very far in the past, then evolve that state forward in time to some infinitely future time using the full standard model Hamiltonian. And then I perform a measurement of some final state T. So I perform an overlap of this evolution operator, and the square of that would be the probability to find a given final state X, given that initial state, say, that was available at the LHC. So if I could do this calculation, I could literally produce or predict the probability, the distribution of events that we see at the LHC. So a couple of processes, a couple of comments here. Now, this is clearly a quantum physics problem. I mean, after all, the standard model is a quantum field theory. And also, I should mention, this is not something that's even remotely feasible using classical computers, and I'll show you throughout this talk why that is, if we wanted to do this calculation. But it would totally revolutionize how we can compare experimental collider measurements with theoretical predictions. Essentially, nowadays, as I already mentioned, we only use observables for which the model dependence that we have in our parton showers sort of is only a small effect, if we want, or a subdominant effect. So this is sort of what I want to do in my talk. In the first part of my talk, I want to tell you how I could, in principle, set up a calculation to calculate a scattering process, as I said, and then very quickly show you that this is completely impossible. It will never happen. In the second part of my talk, I then want to introduce the concepts of effective field theories to sort of alleviate one of the main problems that I showed you was essentially limiting the calculation up here. But then, as we see, this is still not enough. Even with all these simplifications that we do, and as I'll show you, the problem has become a lot simpler, but it's still totally out of reach of classical computers. And this is then when I go in my last part of my talk to quantum computers and try to tell you that I think that it is potentially feasible to do such calculations, really first principles calculations on a quantum computer. Okay, so let's get started with the first part. So I already showed you this slide, right? Or this equation. So this is the S matrix, and this is the object we want to compute. And the problem with this is, so let's for a second forget about the standard model, and I'll only come back to really gauge theories later. And let's actually try to compute a scattering process like this in the scalar field theory. I do understand this is not as complicated as the standard model, but it's a good starting point. And at least many of the problems that I'm alluding to are the same between gauge theories and scalar field theories. So one of the big problems here is that, of course, there's the field theory. So all elements in this expressions are written in terms of fields phi of x in the scalar field theory. But the problem is both the position x and the field value at each point in x are continuous variables. So that means that this Hilbert space is actually an infinite dimensional Hilbert space. And this is the first thing you realize why this problem is really difficult to do. And I should mention we can, well, I'll make that comment in a second. So there is one thing that we do all the time when we have this continuous space that we're dealing with, namely we go onto a lattice. So we only look at the problem at discrete points in space, and then hopefully, make the number of points bigger and bigger and extrapolate to what is called the continuum limit. That means we're going onto a lattice. We're going towards a lattice field theory. And then the second thing we will do, and I'll show you that, is we digitize the field value phi of x. So instead of using continuous set of field values, we're actually going to use discrete field values. So we only look at the field values at certain points. This is actually not so, this shouldn't worry you that much, because actually every classical computer digitizes numbers, right? We have the real numbers as a continuous set of numbers, but an actual computer does not deal with a continuous set of numbers. It deals with, say we have a 64-bit computers as we nowadays have, it deals with 2 to 64 discrete numbers, and then we interpolate. So this digitizing is actually something that we do already all the time. And it's just, we'll do that in this problem as well. So now we have to see how big, and I should mention, this problem is not as easy as normal things in lattice. You've heard, I'm sure, many times that we're doing a lattice field theory. The problem is that in traditional lattice field theory, we're using importance sampling to sort of sample the path integral. And that is something that is not possible in these real-time problems. So, and this will come, this is why this problem will become really hard. Okay, so let's try to understand this a little bit more. So let's, as I already said, instead of having a continuous field phi at each continuous position x, we put a digitized field phi n, a discrete point xk arranged on a lattice. So let's set up a little bit of notation. Here's my lattice. I'm drawing it in 2 dimensions. Let's say the distance between 2 lattice points, let me call that little l. Let me call the total size of my lattice, capital L. And of course, the number of lattice points. So the capital L, the size of my lattice, is the number of lattice points times the lattice spacing. And then finally, I put a field at each lattice point X, and I will use n digitized or n phi digitized field values. So you can now convince yourself that the Hilbert space has a dimension, the number of field values at each lattice size site raised to the number of lattice sites. And the number of lattice sites is the number of lattice sites per dimension, which is n raised to the dimension of my problem. Okay, but once I have this, now I have a discrete Hilbert space. States are vectors, operators are matrices, so the problem is actually reduced to matrix multiplication, right? So this problem here, in this theory, in this digitized lattice field theory that I set out, is very easy to describe what you need to do. Namely, you need to create an initial state vector that corresponds to 2 proton wave packets. Never mind how we do that right now. Then I need to compute the matrix, that's that evolution matrix. Okay, again, never mind how we actually do that in practice, but it is just the matrix. This is the vector, this is the matrix, and that state is another vector in the space. And so this is really just matrix multiplication. I get a number out, I get an amplitude out for this. I take the absolute value of that amplitude squared, and that's my probability. Okay, conceptually, very, very easy to do. So let's try to understand why is this and why have we not done this yet? Well, there's one important thing you have to know about lattice field theories, and that has to do with how many lattice points do I actually need. And so, and you have to realize that the energy range, not range, that can be described by lattice is given by this equation. So let's understand what this equation is. I'm saying here is the largest energy I can describe on my lattice is given by 1 over the lattice spacing. So you can actually understand that very easily because a high energy or the energy of a mode is inversely proportional to its wavelength, right? And the smallest wavelength I can fit on a lattice with a given lattice spacing is, it can't oscillate many times in between my lattice spacings because I don't have any points to resolve that. So the largest energy I can resolve is a wavelength that has wavelength of order the inverse lattice or of order the lattice spacing. That tells me the highest energy I could do. Conversely, the lowest energy or the largest wavelength I can see is a wavelength that's the size of my lattice, by the length of the capital L, which is given by n times L. So that means this is the energy ranges I can describe in a lattice that I set out. And if I want to describe, I have to choose my lattice spacing and my number of lattice points based on the energy range that I'm trying to describe. So now let's say I want to describe the full range of the LHC. So, we need to go up to 70 eV. And, maybe we want to capture hadronic physics. So let's say we go down to 100 MeV or something like this. So below the QCD scale. That needs 70,000 lattice points per dimension. Now, we live in the 3-dimensional world. So that requires order 10 to the 14 lattice sites. That's a lot of lattice sites. And now let's say I need 5-bit digitization. I will argue a little bit later, or I'm not sure how much I'll actually say about this, but it's actually a fact and that you can understand that at least in scalar field theory, you can get away with relatively small digitization. So 5-bit digitization gives you a pretty good answer already. So I need like n5s of order 32 lattice sites. But that means the dimension of my Hilbert space is 32 raised to the power of 10 to the 14. Now, that's an unimaginably huge number, right? Not 32 times 10 to the 14, 32 raised to the power of 10 to the 14. So clearly, I no hope of ever doing this calculation. I probably don't have enough storage in the universe to even just store a matrix with 32 raised to the power of 10 to the 14 squared doubles in a matrix. Okay, it's completely impossible to do this calculation. So we need to bring this number down. And what you can see, what drove this number is that energy range that I'm trying to describe. So we need to reduce the range in energies that I'm trying to describe in order to make this problem simpler. And that is where effective field theories come in, because that's exactly what effective field theories are designed to do. They try to focus on the problems at a given energy scale. So let's look again, what is happening at all these different energy scales? So a typical LHC event really involves very different energy scales. So what I, in the end, after most of the times, is a really short distance process. You know, say the collision of two quarks and then producing two top quarks, or something along those lines. These are scales that happen at those TeV scales that I want. This is happening the shortest distance scales that I'm trying to get at. But then, in order to have a whole event, these additional particles, say these top quarks and so on, they can radiate other gluons, which can then radiate more. They can decay, say, in a bottom quark and a W boson, and so on. So that's happening. And then at some point, these particles will shower more, radiate more particles, and then hadronize at some point. That is happening now at energy scales of order lambda QCD at a few hundred MeV. Okay, so what I'm after when I describe this whole process, describe all of these energy scales at the same time. And this is what requires a huge range in energy scales. However, what you have to realize that really, I don't need a quantum computer or any, we have no difficulty of predicting these short distance processes. We use perturbation theory for that. We all learned that in graduate school, how to do that. And people have gotten very good at that. For the most important processes, say the Higgs production, we've now gone to third order in perturbation theory. We have percent level predictions of these short distance processes. Okay, so that's not where a problem comes in. A problem comes in at these hadronization stuff, these low energy physics. And so what I should do is I should try to separate these scales from each other. So I'm telling you, there's parts of this process that I can calculate perturbatively, and there's other parts that I cannot calculate perturbatively. If I could break this apart and figure out how do I combine the stuff that is perturbative with the stuff that is non-perturbative, then I could try to go out and only do the non-perturbative physics and use traditional perturbative techniques for the short distance processes. And that is precisely what effective field theories are designed to do. In a collider physics at the Large Hadron Collider, many processes can be separated into three main categories where processes happen in three main categories. They're sort of the short distance process, which I just described to you, say these the production of these two top quarks. And then these top quarks and these particles fly apart at really high energies. And then they radiate additional particles, as I said, but from the way QCD is set up, that radiation is happening at small angles predominantly. So really what is then happening, a second process, is sort of the radiation of particles at small angles from these energetic particles, and they then produce jets of particles. And that's what we see in colliders all the time, jets of particles. And then there's a third a set of physics that is happening, third realm of physics, which is soft particles that can sort of communicate between these different jets. And one important thing here is that these three processes are happening at very different energy scales. The hard process is happening at some scale Q. So Q here is the TeV scale that I have in mind. The collinear physics is happening at the scale of the masses of these jets. And sort of a typical mass of the jet at the LHC is like hundreds of GeV, not TeV, but 100 GeV, something like this. And the soft physics here, you can work that out, and I'll have a little bit more on this from Soft-Collinear effective theory, is happening at a scale that is given by mj squared over q. Now, as I already said, the typical mass of a jet is much smaller than the typical energy of these particles produced in these high energy collisions. So you have a very large hierarchy of scales. And that is precisely what effective theories are set out to exploit. So what I'm now going to argue is that we can use effective field theories to separate those scales from one another and calculate physics at those scales individually, and then combine them back into a cross-section. So what are effective field theories? Probably not all of you have studied effective field theories in detail, but probably all of you have learned this, at least at some point in your career, namely that is, I have a charge distribution and I'm trying to measure the electric field at some distance away from that charge distribution. Okay, so let me call the size of my charge distribution capital L, and let's say I want to measure the electric field at distance r away from that charge distribution. Notice that there's one extra positive charge, one extra red charge in here, then there's a blue charge. So if I do this measurement and I try to compute these field lines, it actually looks pretty complicated. I would have to, if back when I started in Berkeley, Dave Jackson was still alive, and he probably could have solved this problem for me. But this is a difficult problem to solve. However, you all know that if I actually look very far away from this charge distribution, then the problem becomes a lot simpler, right? It actually starts to look like just radial field lines. Because really, I can't resolve the details of this charge distribution here. The only thing I still know about this charge distribution is one extra positive charge in that, and that one extra positive charge creates that divergence in the electric field, which gives radially symmetric field lines. So for R, once the scales separate, the problem becomes a lot simpler to solve. We also know that I can actually systematically include corrections in here. If I want to have more corrections, more precise predictions out here, I don't just include that there's a single charge in here, but I can use that there's maybe a dipole moment inside of here. And if I want more correction, I can use the quadrupole moment of this charge distribution. But I don't need this essentially principle infinite possibility of distributions inside the charge distribution. All I need is a few numbers to characterize this problem. And that's really what this is a well-known scale separation. It's known that this really simplifies problems significantly. So the potential that you get is just Q over R. That's the simplest one that I have. And then if I include a dipole moment, there's an extra term in here. Quadrupole moment, there's an extra here. But you can see that as R goes, so X is of order the size of my charge distribution, R is the distance. So if R is much greater than L, then all these terms are suppressed. So there's some short distance physics, Q, dipole moment, quadrupole moment, and long distance physics, which is kind of the response to that. And that's really all effective field theories is. It's trying to separate the short distance from the long distance physics. Now, soft-collinear effective theory is a theory that we designed now more than 20 years ago to essentially separate the scales that we see at the Large Hadron Collider. So I already told you that there's two types of particles. There's collinear particles that have large energies but are at small angles relative to one another. Those are called collinear particles. They're in the same direction as a jet. And then there's these non-energetic particles that go anywhere, but they are soft particles. And I already told you that this lives at a scale mj, this lives at a scale mj squared over q. And so SET is essentially an effective theory that really sets out that works in that limit of infinite scale separation. And it's a theory that is now used all over the place. You can essentially define individual degrees of freedom for different collinear particles. Soft particles, you have individual fields for all of this. You can write down a Lagrangian that describes how collinear particles interact with soft particles, and so on. I'm not going to go into any of the details here. But SET has been incredibly successful in the last 20 years. It's used in many different fields of physics, from understanding formal aspects of QCD to heavy ion collisions, to quarkonia physics, parton showers, and so on. What we use it for in this talk is a proof of factorization, just showing how I can take a cross-section and split it apart into individual pieces that live at different energy scales. And so in particular, and again, I could give probably a whole lecture series on how to do this, but let me just give the final result. Essentially, what you can show that for observables, or for events that are jet-like, okay, not all observables are like this, but many observables have this jet-like properties. Such cross-sections of such final states can be written as a hard function. That is something that describes that short distance nature. As I said, this is perturbatively calculable. And then I have a jet function that describe how energetic particles radiate more other energetic particles. And then there's a function that is a soft function that describes how sort of these different jets interact with one another via soft radiation. And now remember, so I think the most interesting function here is the soft function, because the most complicated object that sort of talks to the whole event. But let's try to understand what is the energy scales in the problem. So remember, I already told you that sort of typical jets at the Large Hadron Collider, the highest energies maybe have order TeV scale energies, have order 100 GeV scale masses. And then if you look at what is the energy scale of the soft function, the typical energy scale is 100 GeV squared over a TeV, which is 10 GeV. Okay, so that means my I need to describe my soft physics up to scales of order 10 GeV. Now, if I want to have non-perturbative physics in there, I want to describe now ranges maybe from 100 MeV to 10 GeV. But instead of our range in seven, almost 5 orders of magnitude, we now only need about 2 orders of magnitude in energy scales, right? My number of lattice sites to describe this physics is 100 in each dimension, not 70,000. Raise that to the 3rd power, you have 10 to the 6 lattice sites. Now that's still a lot, 1 million lattice sites, that's a lot of lattice sites, but it's a lot less than 10 to the 14 for sure. Now that being said, so as I already said in the beginning of my talk, I will simplify the problem significantly, but I went nowhere near enough because honestly, 32 times 10 to the 6, for all intents and purposes, is still infinity. Right? It doesn't really help 32 times 10 to the 14. Yes, it's a lot bigger than 32 10 to the 6, but no hope of ever computing matrices of dimensionality 32 raised to the power of 10 to the 6. Right? It's still impossible to do this calculation, which is why essentially nobody's attempted to do a calculation like this. So why am I talking to you about calculation like this? Well, because I believe that quantum computers can actually have something to say about that. Okay, and this is where I want to go in the remaining maybe 20 minutes of my talk. So maybe before I go there, let me pause for a second, see if there's any questions. Okay, if not, let me continue to go on. And so one of the seminal papers about quantum computers for high energy physics, or also for nuclear physics, essentially for field theories, was this incredibly influential paper written by Stephen Jordan, Keith Lee, and John Preskill. It was published, it's remarkable that that was published in the same year that the Higgs was discovered. It's more than 10 years ago. You have to remember back then, quantum computers weren't a pipe dream, but we were nowhere near at the level where we are now. And essentially what these 3 people showed is that, and they did an example of a 5 to the 4 theory where they really worked this out in detail, where they really showed I can actually compute this whole S matrix that I gave you with resources that are logarithmic in the size of my Hilbert space. So this is, we usually cite when we give, say, a talk about quantum computing to lay people, Shor's algorithm is sort of the traditional algorithm of exponential speed up of a quantum computer. This is also exponential speed up, right? So this brings my size down to a logarithm. And we all know how powerful logarithms are. Namely, if I take my Hilbert space, 32 raised to the power of 10 to the 14, as I said, that's an unimaginably large number. But the log of that, okay, it's still a large number, but 5 times 10 to the 14, I can at least write on a piece of paper, right? It's a 5 with 14 zeros. And so I think it is hard to overstate how important this paper was for this kind of work. However, that being said, I think it bears to some degree almost no relevance, at least in our lifetime, on computing things for the LHC, because I still need 5 times 10 to the 14 lattice sites, okay? And now if I need, number of qubits. Okay, this is logical qubits. Now we can argue how many physical qubits I need, but this is not going to happen. Even if we keep having this tremendous progress in quantum computing hardware, I doubt that any of us will be alive when we have computers with 10 to the 18 qubits in them. So it's still totally inconceivable to have a system of this size in a lifetime. I should, by the way, mention when these guys wrote their paper, they anticipated scattering where the energy of the scattering is of order the mass of the particle. So I can actually get away. There is no hierarchy of scales, and I can get away with a really coarse lattice. Okay, but if you try to take this, so my point is, if you try to take this and then compute things for the LHC, this is just not enough. This is just not going to get us there. But this is already what I've mentioned before, right? For most observables, we're not really interested in the most general high energy process. So, this paper that they said can predict any final state. It's literally an event generator. I start with 2 protons, I let some quantum algorithm run, and then I collapse my wave function, I find some state. And I find that with the same probability as with which an experiment would find it. But we're not interested typically in the most general observables. We're interested in observables usually with energetic particles that are produced in some resonance. So we're interested in events that contain a relatively small number of jets. Second, I already said this as well, is perturbation theory works incredibly well for high energy processes with a limited number of final state particles. So there's really no reason to try to use a quantum computer to simulate the TeV scale physics at the LHC. We have other techniques to do that. So we should use a quantum computer only for those calculations that are not possible using known techniques, and particularly using classical computers, right? After all, maybe I can't imagine the future, but I doubt that in raw computational power, as in like doing the same algorithm on a quantum computer and a classical computer, I bet a classical computer will always beat the quantum. We need to find something where the quantum computer really has a true advantage over the classical one, ideally an exponential advantage. So what I'm going to argue here is that we want to combine quantum computing with effective field theories. And this is essentially what we set out in this PRL that I mentioned. So what we attempted to do, let's compute the soft function. What would it take to compute one of these ingredients in this factorization theorems, which is a true non-perturbative quantity, right? So what I'm trying to compute here is there is some operator, which you actually work out what the soft function is in field theory and the effective field theory. And what you find, it is some time-ordered expectation value of 2 Wilson lines. So what a Wilson line is, it is essentially I write it here, it's a path-ordered exponential of a field along some line n, which is some world line, some fixed line. And in this case, for the problem that we have at hand here, this is a line that lives, it's a light-like line. And you can understand that because what these Wilson lines are describing is how these ultra-energetic particles move through a bath of soft particles. And if I have a really energetic particle, it essentially moves with the speed of light, and no interaction with soft degrees of freedom can change the direction this particle is moving, because after all, it is essentially infinite energy. And so that means it's moving at fixed path, light-like path, and fixed direction. And this is just what comes out of the effective theory, but it is sort of relatively easy to understand intuitively. So these Wilson lines essentially describe 2 jets, one moving in the positive z direction, the other one moving in the negative z direction. And what I then need to compute, this is the operator, and I need to compute what is the, say, the expectation value of the vacuum of my field theory if I act with this operator on it to go to some final state that includes some soft but non-perturbative degrees of freedom, say some pions and kaons and protons or something. So this is a true non-perturbative object that I have here. But as I already said, the typical scale in this process is of order 10 GeV. So I need only quote unquote, 1,000,000 logical qubits. Now I should say, of course, I do understand 1,000,000 logical qubits is still an enormous amount of logical qubits. But I think there is a hope, if things develop, that we could actually get to that point, not in 5 years, probably not in 10 years, but maybe in 20 years or something, 30 years. I don't know. It really depends a lot on the progress in hardware and so on. But I think this is at least something that is not just silly to think about, whereas I think 10 to the 14 is kind of silly to think about. So the question then becomes, if I want to compute this object, how do I do this on a quantum computer? And the first thing I need to do, well, how does this object look like on a lattice? Well, on a lattice, what I have now, so remember what I'm doing here, I'm taking an integral along some path, and I'm evaluating this field phi at n times s. So n times s is a 4 vector that has a time component s and has, say, the z component in position s. But now I'm living on a lattice, so I don't have a continuous value of S anymore, so I can't integrate over it, but I sum over the lattice points that are hit as this Wilson line traverses. And so if you work it out a little bit, you figure out that this Wilson line Y, that was remember, that integral here, becomes essentially the sum over all lattice points. They're now, I'm to change notation on you. What used to be little l for the lattice spacing is now delta x. And I evaluate this at the time equals to x minus n0, where n0 is the point where I started from. Okay, so this is essentially what the Wilson line is. It's a field evaluated at lattice points that are going where this line n hits the lattice points, but then the time has to be evaluated the same time as the x's, right? It's moving at the speed of light. Now you can take this expression and rewrite it a little bit. So you realize that each term in this exponent, there's a sum over exponents, which of course, since the fields phi at different points are commuting with one another, I can write a product of exponentials. But each term in this exponential is evaluated at a different time. But now I can use time evolution to actually put this all at the same time. So if you work this out, but I hope this is somewhat intuitive, you essentially find that this operator becomes an exponential evaluated at some field values at the center, then you time evolve forward. You start here, you time evolve, and then you hit the next two lattice points, you time evolve again, you hit the next two lattice points, and so on. So you hop through the lattice this way. And so you alternate between exponential field operators and Hamiltonian evolution. And so now we can set about, well, can we actually, so remember our goal is to implement this operator on a quantum computer. So now I have a lattice version of this operator. And now we have to see, well, can I actually write down these expressions of these operators? Can I write down circuits on a quantum computer? Can I implement that on a quantum computer? And in particular, can I do that with logarithmic resources? Remember, it was crucial that that I can do calculations with logarithmic resources compared to the size of my Hilbert space. So that is still something I need to show. However, for the Hamiltonian evolution, we can just directly use the results of Jordan, Lee, and Preskill, which essentially work this out. And then there's subsequent papers by Martin Savage and others. And we've also worked some details out in our paper. Essentially, the whole Hamiltonian, there's a Hamiltonian, if you work it out, there's a term that goes like the phi squared term. And then there's a term that is the pi squared term that comes essentially from the time derivative of the fields. And this is the Hamiltonian that I need to implement for these objects, for these time evolution objects. And the point is that I can do this. I can actually work out quantum circuits that implement this Hamiltonian. Essentially, they all look in the end like objects like this strung together. And there's only logarithmically many. I mean, there's only as many of these objects as there are qubits in the system. And so this is something that I can implement, as I said, with logarithmic resources. So that gives me the Hamiltonian. I still need to figure out how to do these exponentials of field operators, but that is actually even easier because they are just in the basis, in the field basis. These are just diagonal in the field values, and this is actually, implementing this object here is actually just a very simple thing. It's just n single z rotations that I can apply. So putting all of this together actually allows me to implement the whole Wilson line operator, and we can literally write a current or a circuit for this whole object down. So that means now that to compute this object here, I need to do the following. I need to create, I start on some qubits. I need some circuit that creates the vacuum of my quantum field theory. That is actually not a trivial problem, but there are various ways to do this, and we have some papers on this as well. So I have not told you how to do this, but just believe me that this is possible, again, with logarithmic resources. to create essentially, so this, if I act on my initial state where all qubits are 0, if I act with this object on it, I create that state omega. Then I act with this operator on here, which is just some circuit, which I call UI. And then I measure out some state X by acting with U dagger X. On this here, then I perform a measurement, and the frequency with which I measure this state and the all 0 state will give me that expectation value of that object. And so really, if I want to simulate the soft function, there's now a very simple step. You start with all qubits in the 0 state, you apply an operator, this is what I just said, apply an operator U omega that creates the ground state, apply this operator that acts with the Wilson line operator, perform the inverse of Ux, creating the state X, act with it on here, and then you measure and count the number of times all possible qubits are in the 0 state. And that gives you the non-perturbative soft function. Now, in order to do this, I have a few more details here on how to actually do this. We use Suzuki-Trotter implementation of the Hamiltonian. So there's various technical details to get this done, but it is actually possible. Let me show you a couple of checks that we did, in particular to see how the trotterization works. So what we did here, I created a state, and then I acted with, so I just wanted to see, do I actually get the right, is my Hamiltonian doing the right thing? So if I act with a Hamiltonian like this, a controlled version of this Hamiltonian on this, what I should get out is 1 plus the expectation value of this object here, and this guy is the ground state. That should just give me the energy of the ground state in a phase. So e to the I times the energy of the ground state times t. So this is an oscillatory behavior. And what you can see here in the dashed lines are the exact predictions, and in red are the simulated prediction with trotterization. So this works with the kind of trotters. Here we used 5 trotter steps to do this simulation. We can actually, and so one nice thing about this simple theory that I have here, where I have this in terms of scalar fields, this is actually a problem I can solve. The lattice theory I can in fact solve analytically. Now, this is not something I can do in an SU2 or SU3 theory that we're in the end after, but being able to solve this analytically gives me a great way of comparing my simulations to an analytical answer. So this is a lattice result, but without digitization. So this is the full field theory, full lattice field theory calculation that I can just work out analytically. Okay, so before I conclude, let me just show you some results. So the first thing is that we did is we actually checked. So here's my analytical calculation that I had here. Remember, I told you this is with the non-digitized field values. And remember, right at the beginning of my talk, I told you even using just 5-bit digitization is good enough for scalar field theories. And I said I wouldn't really talk too much about it. Well, I just want to show you that this works. So this is the analytic calculation with full continuous field values. Let me do now the calculation, the digitized calculation. This is if I use a single qubit, so 1-bit digitization. So you can see I'm not quite on the blue line. This is 2-bit digitization, so only 4 field values. And this is 3-bit digitization, so 3 qubits per lattice site. And you can already see we have almost perfect agreement. You can actually understand why that is. There's exponential convergence in the number of qubits per lattice site. Okay, so now we can ask, now let's actually do my full simulation that I said. And so now I have to see what is actually, if I run the algorithm that I have and actually make a prediction of this analytic result, but with a full digitized calculation that I've told you. And there's a few, this is not exactly the result that I had earlier, but this is now having to do with my state preparation. Is also not exactly the right state preparation. So anyways, this is the kind of result. This is what I'm after. Okay, so this is, I think we have here 2-bit digitization. And so let me see, and I have 3 lattice sites. So this is the simplest problem you can imagine. I have 3 lattice sites, 1 dimension, 3 lattice sites, 2-bit digitization. So I need 6 qubits to do this calculation. So this is a simulation. But then we said, let's actually run it on a quantum computer. Let's actually see what we get. And this is what we got. So, you can see, depending on whether you're an optimist or a pessimist, I think you have two different conclusions for this. You can say, the optimist would say, look, this is great. It has the right behavior. It starts high. It has the right trend, and so on. But the pessimist would say, come on, you're totally off, right? So what's going on here? Well, actually, a lot that's going on here is noise in my quantum computers. And so what we actually did try to do at the time, use sort of noise mitigation that was available at the time. And we corrected for noise a posteriori, and then we got these black results. So I'm telling you that the difference between green and black is essentially known noise in my quantum computer that we know how to get rid of. And that all of a sudden, I think, looks very impressive. This is actually now a real quantum computer, right? This is run on an IBM Q quantum computer, Manhattan. It was, and we predict, or we agree with the simulated result. So that at least shows you that for these small systems, I can really do these kinds of calculations on a quantum computer. Okay, I'm pretty much at the end of my time. I just want to show you in a few cartoons of some of the work I've done since that work. Because the goal here is, as I'll, this was a scalar field theory, very small system sizes. And of course, we want to go to more realistic field theories. So I'm just giving you some cartoons here of what we did. I started to do some work. This work was with Dorota Grubowska last year, end of last year, where we try to go towards gauge theories. And we try to actually ask, what is the best way to simulate gauge theories, and particularly if I want to go to the continuum limits, where you need to work at small couplings. Essentially, most of the previous work on gauge theories was focused on work in the large coupling limit, but because of the way RGE flows happen, you actually need to do calculations in small couplings in the continuum limit. And many of the formulation that existed at the time are really not suited for this. And we did some work, I'm not going to give you any details, that essentially made calculation of small couplings much, much more reliable. We also dealt with possible exponential scalings in systems. So if you actually look at these U1 field theories, there's one particular term in the Hamiltonian that actually naively looks like it requires exponential resources to do exponential in the size of my lattice. And so we worked on trying to get rid of, to break that exponential scaling. And all we're showing you here is sort of a connectivity between qubits, which grows exponential here. And after essentially our field redefinition that we did, we got a logarithmic connectivity. So this is all about formulations of field theories to make them better. And we have to understand how to deal with these field theories before we can go and actually try to simulate a process like these Wilson line operators. We also had papers on trying to mitigate noise. So remember, I told you what I showed you was the noise that was available at the time. There's a lot of research that has happened since then on making better and more reliable noise mitigation schemes. We have worked on that as well. And then we also worked on some very practical things, like how do I actually, remember I told you it's sort of known how to prepare that ground state of my field theory. Well, it is true there was a paper that told you how to do it in principle, but nobody actually worked out the circuit of how to do that in general. And so there's a paper that we did where we actually worked out these circuits. And that's an example of that. So the goal of this program is to have a first computation of an effective field theory matrix element in a non-abelian gauge theory, right? That's where we have to go to. And of course, really by non-abelian, I mean SU3. That's the ultimate goal, because that's what nature is after all. So that's where we're going. And there is various things that we have to do, but let me just summarize here because I'm out of time. So what I've tried to do in this talk, I've tried to argue that the most promising avenue for quantum computing, and actually computing for collider physics, like there's many other promising avenues for quantum computing, of course, but quantum computing to connect with the collider, the high energy physics collider program, is to compute non-perturbative matrix elements in an effective field theory. What I've showed you is that by using these effective theories, the number of qubits, or the number of qubits I need to simulate the effective theory, is many orders of magnitude lower than if I were to try to simulate the full theory. I've showed you that we can get a relatively simple circuits that actually compute these effective field theory matrix elements. And at the end, I've showed you that in a very simple system with 3 lattice points and 2 qubits per lattice site, we can actually reproduce, have a real quantum computer do a calculation that is actually looking remarkably close to the analytical result. So I just want to end here with showing all the people. These are not all people who've contributed to this particular project, but all the people that I've collaborated with in Berkeley over the years in quantum computing. And I'll just leave it here and I see if there's any questions. Thank you.
Thank you very much for this very nice talk. Are there any questions from the audience? Ever raise your hand, please, unmute. Please, David.
Hi, thanks, Christian, for that very nice talk. Let me know if the audio is okay for me.
Yeah, I hear you well.
I had a question that sort of came into my mind as you were talking about that final test, looking at the number of qubits used for the digitization and showing that exponential convergence to the analytically computable result for a fixed lattice size. And I started worrying what is going to happen if you try to start making that lattice size bigger. You will have more degrees of freedom that are contributing to these observables, adding up, and digitization errors might start piling up in that context. I wonder if you've looked into that.
Yeah, it's not actually. It is not. So the important thing that these Hamiltonians are essentially only bilocal. So the Hamiltonian, the full Hamiltonian, certainly in a scalar field theory, this is certainly true, is that it's only bilocal in lattice sites. So the only terms you ever have is a term that connects 2 lattice sites to each other, and they're local. Okay, so it only connects the nearest neighbor sites. And so, and that is the whole Hamiltonian. And okay, now we have to worry about trotterization errors and so on, right? Because I still have a sum of many terms, but these terms they actually commute with one another. So there's no actual trotter issues going on here. So I don't think that there is in these, certainly in the scalar field theory case, I don't think there's an issue going on. Now, as I said, if I go to more complicated field theories like this one, there's actually one term in here that actually connects all lattice sites together, at least in the, in one particular formulation of a U1 of a U1 gauge theory. And that was actually a problem that I don't think people had fully appreciated yet. There was a term in there that was actually scaling exponentially with the lattice because it connected all lattice sites together. And here we actually did have to work pretty hard to break that exponential scaling. So I think it depends a little bit on the theory, and it is possible that we haven't seen all the issues, right? There, for example, there's no real, there's been no real study QCD in 3 dimensions. Nobody has attempted that at all. And so, while we believe that there's no minds hiding somewhere, but you never know actually until you do it, right? So
yeah, as a quick follow-up, the Hamiltonian is certainly bilocal, but that Wilson line you're looking at is going over a larger number of sites. So could it depend on the observable as well as the Hamiltonian?
So, but in the end of the day, if you look at it, it's just, right? So it is products of fields, and the fields at these different lattice sites, they commute. So again, I can actually, this is essentially, each of these terms is just, I have individual registers for each lattice site, and each of these objects, so I can run them in parallel over all the things together. They don't actually communicate, right? This is, again, only, actually, in the scalar field theory, these 2 things even commute, right? These 2 things, these 2 points. So this is just products of exponentials, each only acting on a single lattice site. So it does not actually couple anything.
Thanks.
In this particular situation.
Are there other comments or questions? We have a couple of minutes. It doesn't seem so. Okay, last call. Okay, then let's thank Christian again for this very nice talk.
Thanks so much, Simone.
And I would ask Raffaella to set up the slides to announce next talk, next Quantep seminar. Yes, okay, thank you. So actually with the new year, we are starting a new kind of series of seminars, kind of more tutorial seminars. So we will alternate more advanced and research updates, Quantep seminars as we have done until now, with some tutorials to set the ground for students and even colleagues that wants to enter in the research or get inspired to start on more basics level for studying or applying quantum technologies, quantum computing to high energy problems. So next January, we will have Pietro Silvi that will start with introducing tensor networks for Hamiltonian lattice gauge theory simulations. And with that, next one, I would like to thank our organizers of this series, Yasser Omar, Andres Ambainis, and Joao Seixas, and of course, those that make this possible, Rafael and Matteo, and wish you a nice break. We can start probably with that by now, and see you in January. Goodbye.
Thanks so much. Bye, everyone.